Okay, this is going to be a little flipped assignment on stoichiometry, and it's a slightly different look. And the reason we're going to show you a slightly different look is because with this model, you will be able to not just come up with an answer, but to do a much better job of predicting before, during, and after everything that happens. And as much as students sometimes don't like it because it takes a little bit more extra work, it's going to benefit you tenfold down the road when we get into equilibrium, limiting, excess. There's a million ways in which this can happen. Step number one, stoichiometry, again, is given how much we have, how much are we going to end with, you have to have a balanced equation. That is going to tell you what we're starting with, what we're going to end with, how they rearrange. It gives you the ratio of the particles or the ratio of moles. If you don't have the balanced reaction, you may as well give it up and just quit. So let's see what we're talking about with this slightly different method. Okay, so step number one, here's an example that we may be doing in class as a demonstration or a lab, and it's magnesium plus oxygen gives magnesium oxide. And what they're trying to show here is that for every 2 atoms of magnesium, you use 1 molecular substance of O2 gives 2 formula units of MgO, or that could be mole ratios. Now, anytime we're trying to make a good prediction, we want to carefully just sit back and say, what happens before? Before, usually what we have is some reactant and no products. Second, we need to know about the change. You're going to use up the reactions, and in the world of math, we call this, by using up, we put a minus sign, and then you're going to gain some of the products. And then afterwards, what's left on both sides. And again, this gives us a much better picture of what's happening in the entire reaction, and this will serve you much better down the road. Okay, so when we start to do this, we're going to be using a table, and this is called a BCA table. So here's a sample problem. Hydrogen sulfide gas, which smells like rotten eggs, burns in air to produce sulfur dioxide and water. So we've got the reactants and the products. How many moles of oxygen gas are required or needed to completely burn 2.4 moles of hydrogen sulfide? Step number one, if you notice, the first thing that I did was you have to have the balance equation. And then the second thing I want you to see here is once we have the balance equation, we set up a table that says this is where we are before, this is what we start with before, there's going to be some change, and there's going to be whatever we get afterwards. So again, the balance equation, before, change, and after. Part 2 is we just fill in with what we know initially before we do any calculations. Now if you think about what they did, they just took stuff from the problems and they said, look, before we have 2.4 moles of our H2S. Okay, we have a total excess of O2. Nothing's happened yet, so there is 0 O2 and 0 H2O. Nothing's reacted. Now, we know that some change is going to occur. Okay, and what I just tell students, put a sign here. We are going to use up, lose reactants, and somehow gain products. And that's the symbols that we try and show. And then somehow that's going to have an effect afterwards. So again, it's just before, some type of change, and after. Okay. Next phase, let's take a quick look, this is what we filled in. And if you look, again, there's nothing, we're just trying to say, okay, so let's go back to what we've had. The balance reaction, we filled in the before. This is what we're starting with. We have an excess here. There's nothing here, nothing here. We're going to use up, okay, so it says in the problem, hydrogen sulfide gas smells like rotten eggs. How many moles of oxygen gas would be needed to completely burn? Total combustion. So we're going to use up all of this. The question is, how did they get 3.6? Okay. Well, here's the easiest way I can describe how to do the math here. I always tell students, just ask yourself, to go from 2 moles, to go from 2 moles to 3 moles, what do I have to do? Okay, so let's look. To go from 2 moles here to 3 moles here, how do I do that? Well, it's 2 moles of H2S, okay, H2S times something is going to give me 3. The only way I can do it is to say 3 over 2. So if I say 2.4 moles of my H2S, and I need to get labels and units and all these, but I'm trying to hurry so we don't run out of time, times 3.2, that's how they got the 36, and that's going to be used up. And I'm sorry, 3.6, and that's what's going to be used up. And the nice part about this is because it's a 1-to-1 ratio, if we use 2.4 moles here, I have to gain 2.4 here. And again, we're going to gain. I got to gain 2.4 here. So so again, this change should be here. Now, here's the easy part. What happens in the end? Well, if you can just add and subtract, you're in good shape. So watch what happens. 2.4 minus 2.4 is 0. And excess minus 3.6 is the negative 3.6. This is the moles of O2 that we use. And this is showing over here what we gain, the plus 2.4 moles of my SO2. And this is the plus 2.4 moles. 2.4 moles of my H2O. Okay, so I'm just following this down. So again, we just, the math all takes place here. The only thing that goes in these tables are moles. Now, the last part is, that's nice, but we don't really weigh out moles, and that's why we've got this. And we're talking about oxygen, and of course, now, separately, okay, you can say, how do I go from moles to grams? Because typically, it's grams that we typically have to weigh out in the lab. Okay, so this starts to explain how we do this in the lab. So again, kind of a nice deal here. Let's see here. So the part about this that we're trying to get here is this. If we rephrase, number 1, you got to have the balance equation. Number 2, you want the BCA tables, and by BCA, you get the balance equation here. You want before, change, and after. And that's what, and also with the change, I tell students it's always going to be negative, negative, using the reactants. We're taking away the reactants and we're gaining the products. Part 2 here is we just put in whatever they give us, and usually this is always going to be 0 and 0. And then the last part is we have to do a little bit of math. Okay, and the math is the change. And usually it's the ratio. We use the balance equation to go from moles of whatever we have to moles of what we're finding to. And there's ways to do that. And finally, at the very end, if we just add up the columns, find what we want, we can get grams. Now, if they're only asking for O2, why did I bother with this over here with my like the products and everything? Because we will need to be able to look at the entire reaction before, during, and after down the road. That's it, and please take notes and answer any questions and bring it to class.